Hello everyone, my name is Saria Mghames and I'm here to present to you the work done together with my colleagues at the University of Lincoln in UK and University of Padova in Italy around the topic of qualitative prediction of multi-agent spatial interactions. Our aim is to endow service robots with capabilities to reason and act on the implicit intent communicated from its surrounding. The problem, however, resides in the lack of implicit intent consideration from neighbors in the decision-making of social and service robots. Our aim can have substantial impact on application domains of logistics, domestic, and healthcare, such as reasoning on the need of elders for help in getting a medicine or the need of a worker in getting help in carrying a heavy load. In parallel, service robot should not interfere with conversational groups. Our current work deals with modeling and predicting multi-agent spatial interactions. It's the first time to address the prediction of spatial interactions in multi-agent context and the role of interactions prediction in the navigation pipeline. As for example, the prediction can be used to feed an optimal planner as the model predictive controller for reactive decision-making. Our strategy relies on benchmarking three frameworks. The first one, denoted by FQTC1, takes as input the series of labeled or index interaction representation and generates as output the predicted interactions over a horizon. The second framework, denoted by FQTC2, is similar to the first one. However, it uses a different representation of the interactions. The third framework, denoted by FTS, takes as input the time series of raw coordinates and as output the predicted time series of those coordinates. Then the output gets post-processed for predicting spatial interactions. In order to build the three frameworks, we adopted the following tools. The first one is a qualitative interaction representation, as it is known to be an intuitive approach for interactions description. One way to represent qualitatively interactions between multi-agents is by using the calculus known as qualitative trajectory calculus and denoted by QTC. Since the three frameworks are trained with different loss functions, like the first two frameworks are trained with cross-entropy categorical loss function, and the third one is trained with the root mean square error loss function, we propose the conceptual QTC distance, denoted by dQTC, as metric from the state-of-the-art of qualitative interactions representation to compare the three frameworks. In order to briefly explain what is QTC about, the QTC is presented over the literature in different types. One type of the QTC is the QTC with the subscript C, which is the cross-entropy QTC. And this type of QTC has two subtypes, QTC-C1 and QTC-C2. QTC-C1 has 4 qualitative symbols from Q1 to Q4, and QTC-C2 has 6 symbols from Q1 to Q6. Each single symbol belongs to the discrete set of R3. Q1 and Q2 of both QTC types represent the moving towards away dichotomy between two agents. Q3 and Q4 represent the right and left dichotomy. Q5 represent the relative velocity between two agents, and the Q6 symbol represents the relative angle between two agents. For example, in the middle figure, the two agents, PH1 and PR, corresponding to human 1 and robot, have Q1 and Q2 symbols, minus and minus. For numerical reason, we use -1. Those two symbols, minus and minus, represent two agents moving towards each other, and they will be equal to 0 if both agents are still not moving. In the right figure, we illustrate a subgraph of what is known conceptual neighborhood diagram of QTC-C1 subtype. We represent the subgraph because the whole C&D graph of QTC-C1 is very complex to illustrate it, with 81 possible states in total. This subgraph illustrates the possible transitional state of one qualitative interaction state, which is the central one, minus, 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 minus. In general, each state cannot transition to all other 80 states. Some rules apply. For example, the minus and plus symbols cannot transition directly to plus minus symbol without passing through the zero state. We tested the three frameworks on social scenes as the Jackrabbit dataset collected from the social robot point of view in dense and social scenarios. Jackrabbit was never deployed for human interactions or motion prediction. Hence, we choose the dual attention recurrent neural network architecture from the state-of-the-art for testing. The DA-RNN architecture is a generic architecture for time series forecasting. It benefits from a multivariate data input, an input and temporal attention mechanism. It showed better performance in terms of accuracy for generic time series forecasting, and it allows to incorporate static objects as any other moving body point. Jackrabbit dataset was collected from a 360 velodyne LiDAR and fisheye camera sensors on a mobile robot. We processed the dataset for input and output data generation to the network. The crowded scenes of Jackrabbit can present a computational complexity to the network input size if they are left unbounded. Hence, we follow a clustering technique by generating clusters of radius equal to social distance from the proxemics literature, and this radius range between 1.2 meters and 3.7 meters, and the clusters are generated around each agent. Each cluster is now input to the network, as in the figure here, where the input is time series of index QTC vectors between the central agent and each neighbor in the cluster for FQTC1 and FQTC2 frameworks, while it is the time series of metric coordinates for framework FTS. The output of the network is the prediction of the input series over 3.2 seconds and 4.8 seconds horizons. We choose two scenes from Jackrabbit to conduct our experiments, the cafe scene on the top and the poster station on the bottom. The cafe scene was tested on two clusters of radius 1.2 and 3.7 meters, while the poster station was further used for testing the transfer learning to a different but related scene. The qualitative results on the cafe scene showed that over the shorter term horizon in green box, FTS1 has better performance in terms of lower mean and standard deviation of the metric DQTC on both cluster radius R1 and R2. Over the longer term horizon in blue box, FTS1 has better performance on cluster radius R2, while FTS2 has better performance on cluster radius R1. Overall, the performance of FTS1 on R2 is better than that of FTS2 on R1. The qualitative results on the poster session 2 scene show that over the shorter in green and longer in blue term horizons, FTS1 has better performance on cluster radius R1. For the transfer learning from PS2 to PS1, the red box on the right show the results on the transfer learning to PS1 poster session 1 scene. It shows that all frameworks transferred well over the short-term horizon with best performance on PS1 given by FTS1 framework. And FTS1 and FTS2 didn't transfer well to PS1 on 4.8 seconds horizon, but the best performance on PS1 is given by FTS1 framework again. In our future works, we plan on integrating the FTS1 framework in a predictive planner for logistic applications as the application domain of the project DARCO supporting this work. Finally, we thank you for your attention and we welcome any discussion around this topic.